Okay, in this review problem, this is an example that's, just like one of the homework problems. In fact, it is the homework problem, but for our purposes, I'm going to change this 5 to a 3 so that you can go back and work the original problem. I don't want to work the same problem for you, so this is a slight tweak so you can see what's going on. Okay, so the first thing I want to do is I want to talk about some angles. All right, so if you think about it, what we need are angles, and we can find some on here. All right, first of all, what we need is all the angles from the horizontal. Okay, so here's a horizontal. Okay, do a different color. Here's a horizontal that works for both F1 and R. Okay, now let's put in some angles. This would be theta 1. Okay, this angle, changing the color, would be theta 2. And one last color, green. This angle from here to here would be theta 3. If we know those angles, this problem is actually pretty straightforward. All right, so let's talk about angle theta 3. Oh, and first of all, before we even do that, let me move all this stuff. We'll put it right back in a second. But before we do all that, this is a vector resolution problem. So the assumption is that the resultant vector is the sum of F1 plus F2. All right, I'm not sure if you've talked about this in any of your high school classes or a physics class, but when you add vectors, you add them tip to tail. All right, so here's a vector. All right, color over it. When I add F1 plus F2, I take the original F1 and I put the tail of F2 to the tip of F1, and it gives me the resultant sum. Okay, so when I add these together, you can do them graphically. Tail to tip addition of vectors gives you the result. Okay, so this is, the governing equation is R is equal to F1 plus F2. All right, so hopefully that's clear. All right, so back to where we were. Let me erase this and put this notation back on top. Okay. All right, so we have these angles defined. Let's consider angle theta 3. I want to show you something about that, and I want to show you a trick that you can use and know about, and it'll save you a lot of heartache throughout your engineering career. All right. So we look at theta 3, and he's got this resultant vector that's a 1 to 1, and I think you probably have the intuition that this right here is 45 degrees. Okay, so if on your calculator you did the arc tangent of 1 over 1, you get 45 degrees. But you notice that's not theta 3. All right, theta 3 goes all the way from here to here. So you probably talked about in your calculus class that you have to pay attention to the quadrant of the angle. All right, so this is 45, so I see that I have to add another 90 to get theta 3. Okay, so theta 3 is A10, 1 over 1 plus 90 degrees, okay, where this is in the degree mode. All right, so that requires some thought because you have to do the same thing with theta 1 and theta 2. You have to make sure when you do the arc tangent that you end up with the right quadrant. Okay, or sorry, yeah, with the angle in the right quadrant. All right, so here's the trick. There's a function on your calculator called A tan2. All right, and A tan2 has two arguments. It has the vertical argument is first and the horizontal argument is second. So let me write this down. We'll move this down and over. Okay, we don't need that anymore. Okay, so when I looked at theta 3, if you look at this as an xy coordinate system, all right, to get theta 3, what I realize is that theta 3 is an arctan 2. Okay, so this is a special built-in function. This built-in function automatically takes care of quadrants. Okay, so what I realize is that the y direction I go up by 1. So the first argument is 1. And in the x direction, put a different color here, I go back to the left. That's in the negative direction on the real line. So this would be -1. Okay, so saying that again, here's the vertical, that's the first argument. Here's the horizontal, it's in the negative direction, that's the second argument. That gives you the same answer as what we did right here, where we had to think about the quadrant. So isn't that nice? Here's this built-in function in your calculator where you don't have to think as much. Okay, so let's calculate the other thetas using the same approach. Okay, so by this time, this is a number. It can be stored in your calculator. Okay, let's do theta 2. Theta 2 can be done the same way. All right, but I look at theta 2. Let me clear off some space here where you can see it. Okay, theta 2, you go up. I labeled these wrong. Okay, sorry, this would be theta 1 because it's associated with F1, and this would be theta 2. All right, so if we're looking at theta 2, it's this orange angle. All right, so underneath here, let me clear that. Theta 2 is this angle. Okay, and we see we go down 1, right? It's down, so that would be a -1. And then we go back to the left by 2, so that's also a negative number. So -1, -2. The signs take care of the quadrant. I don't have to think about, subtracting from 180 or whatever would happen in this case. All right. And then the last one's pretty straightforward. Theta 1, it's the arctangent 2. 2 meaning it has 2 arguments. Okay, so we go up 3, and that's in the positive direction, and we go over 2 to the right, which is also in the positive direction. Okay, so that's the hard part of this problem, in my opinion, is getting the thetas right. Say, once you have that, what we know is that R is equal to F1 plus F2. All right, so if we want the x direction, looking here, we know that in the x direction we use cosine to project down. So Rx is going to be R cosine theta 3. Okay, so let's just get rid of that and write the full equation. Okay, Rx cosine theta 3 is going to be F1 cosine theta 1 plus F2 cosine theta 2. All right, so now we have an equation. This is absolute value sign. And we can get another equation by looking at the vertical components. So this is the x component, this is the y component. That's supposed to be sine. Okay, so just x component here, y component here. In this particular problem, we know that R is equal to 850. Okay, so we can plug that into these two numbers. And that gives me two equations, two unknowns. The two unknowns are F1 and F2. All right, so you just solve those equations for this particular case where I've changed the problem. Remember, I changed the problem from what I signed in the homework. All right, but when I do that, I get the solutions to be F1 is, the magnitude of that is 1,680. I think this was newtons. Okay, and F2 is 1,625. All right, so hopefully that will help. All right, I think this would be pretty tedious for an exam problem, so I know you're freaking out a little bit about it because it probably takes you a while to solve these two equations and two unknowns. Okay, so there's a difference between a problem being hard, conceptually hard, and being tedious. This problem is definitely tedious, okay? But conceptually, you should try to simplify your mind, clear your head a little bit. Conceptually, it's just r is equal to f1 plus f2, and then you look at the x component, which usually means a projection with cosine, depending on how you define the angles, of course. And then the y component is a projection with sine. Okay, so it's tedious, but it's not conceptually hard. All right. Hopefully that helps.